Hi, this is Tracky, Research and Practice. It's part one of this series, which is foundational papers. Today we are going to look at AlexNet and Word2Vec papers that were published in 2012 and 2013 respectively, 1 year apart. While these are research papers published, many of us are wary or scared of looking at these research papers because a lot of words, a lot of technicalities, a lot of computation involved in that, and that scares us. So I've included a section on how to read a paper as well. One thesis that we are going to look at this week is, hey, while there are papers being published, we need to understand the trend in them. Okay, and this track is all about encouraging us to not follow the trend but look at what's happening as a pattern in research. Okay, we should ideally be all reading research papers to understand what's happening in that particular field. Yeah, history will always compound, yeah, and it will not arrive as a trivia. It will always compound. So understanding the foundations of why a particular research took place in a certain time frame in a particular region is very interesting. And for us, we are going to read it as a product manager, not as an engineer. Yeah, we don't have to reproduce the whole complete math, the complex complete math. Yeah, we just need to extract what is important out of these papers and how can we productize it, yeah, for our needs. We will look at two papers today, which is AlexNet and Word2Vec, and the one lesson that is common between these two. Yeah, what started the deep learning era that was just 12 months apart. This is going to be our roadmap. It's a long climb, I would say, but hang on with me because it's all interesting. We're going to look at Srinivasan Keshav's How to Read a Paper and take the three phases that he is recommending or passes on the paper on how to read a research paper. Then we're going to look at AlexNet and how it helped vision systems. Then we're going to look at Word2Vec, which helped language models. Finally, the shared vision or that these two shared and a common lesson between them and how can we keep learning from there. I have additional sections 5, 6 and 7, which I'm not going to tell now. Go through the complete video and we are going to come there. Many of us scared that I will show diagrams like this, which are very complex in nature for the research paper. No, we are not going to do that. We are not going to dive very deep into the math and the matrix multiplications, the weights, the convolutional layers, the kernels, the eigenvectors. None of that. We will stick to only the required depth that a PM needs. First one, how to read a paper. Yeah, this is very important because over the next 15 weeks that I promise that I will be posting content on, we need to be wary that there will be a lot of papers that we'll have to go through. Not just for the lingo or the vocabulary, but to understand how today's systems are using the research that happened a while ago. And Srinivasan Kesav's paper says that if you have a paper, don't read it from top to bottom because it will be expensive and it will demoralize you because many of the topics are unknown. You'll do a lot of research on them, you'll be lost, you'll not come back to the paper, you'll find it very taxing. So much so that I also have printed a couple of papers like Attention is All You Need and others. Haven't read a single word. I tried reading, I lost it. But when I followed Srinivasan Keshav's approach, where he says that, hey, take a first pass in the first 10 minutes. In the first 10 minutes, go through the title, the abstract, or the summary, and the introduction, and then look at the titles across. Capture few images in your mind, nothing else. Go to the conclusion or summary, and make a sense of all of this in the first 10 minutes. Don't do any deep dive right now. Even in the second part, we don't do a deep dive. We only go through the important sections which talks about how the processes have been used, what calculations have been done, etc. Third pass is the PM pass. This is where we dive deep. Okay, This is where we need to make sense of the whole paper. Again, if you do not understand certain words, certain references, it's always to park it there, go through the complete paper, and then come back and read them. Otherwise, we are going to deviate from the whole paper and never learn. So, while we get a gist of the paper in this 1 hour and 30 minutes or so, 90 minutes or so, it's always recommended that we have multiple passes on that. Yeah. What happens by doing this is it helps us understand that with each pass, is the paper getting interesting or is it getting boring? Yeah. Many of the papers you'll stop at pass 1, you'll not even go to pass 2 and pass 3. And that's what he's explaining in detail. Yeah. In the pass 1, the first 10 minutes of the triaging, he says that go through the title, abstract, headings, figures, conclusion, and nothing else. Yeah. A good paper puts its whole argument in 1 or 2 plots, no more. Yeah. If it doesn't do that, should we even care about it? Yeah. The next 45 minutes, you're going after the idea, not the ability to re-derive it. Yeah. You're not going to write the whole you're not going to write the whole code or simulate the whole experiment again. Yeah. You need to mark certain sections on, hey, why was this approach taken and why wasn't a certain approach taken? Where does this break? Mark them. Yeah. Interrogate the whole setup. Hey, why did they compare this against? What did they compare this against? And is it a fair comparison and so on? Yeah. So the first 50 minutes or 55 minutes that you're going to do is typically arrive at a conclusion saying that is this paper interesting? Yeah. Will I be interested in more papers? Yeah. The next 30 minutes is a PM pass. Yeah. We as PMs will read the papers. Yeah. But not as an engineer who reads the papers. Yeah. So the engineers also might sometimes stop at second pass, but we as PMs need to go to the third pass. Yeah. We need to understand what are the consequences. We need to see the product, the market, or the moat implications before they become obvious. Yeah. And this brings us to our paper tool chain. Yeah. Many a times we'll try to read these papers, but we'll be lost. Hey, why did we do a certain thing a certain way? What do these certain words mean, etc. Yeah. If we use a separate documentation tool like Notion or something, we will be lost. We will not know why certain words we search. We will not be able to tag it back. That's where a tool like Zotero comes into play. Zotero is a free tool that you can use to bring in papers, uh, tag them, highlight them, make notes, bring in other papers, reference those papers, etc. This is all possible in Zotero, and Zotero is fully open source. You can use it for free until 300 MB of storage space, beyond which you'll have to pay very minimally like $2 per month or $3 per month for additional storage of 2 GB per month. Yeah. There are papers available from Archive, Alpha Archive, Archive Sanity. My favorite, I would say, research scientist, which is Andrej Karpathy, he has written a couple of improvements on Archive Sanity as well. Yeah. And ultimately, Notebook LM is a very good tool where you can pull all these PDFs and say, hey, explain me certain topics because I do not understand the complexity of it. You can listen to a podcast style or audio overview as well. You can argue, you can comment, you can negotiate or bargain on certain strategies also. Yeah, it can become your study partner. It need not be just source of record itself. Yeah. Yeah, these tools don't help you read the paper for you. It rather lowers the cost of the passes. Yeah, it makes you understand the context. It helps you understand what went as a thought behind this paper and so on. Yeah. So the recommended approach is you triage in audio, read in the PDF, and store it in Zotero. Yeah. If you want to hunt more references and so on, go to the Alpha Archive. Yeah, I'll show a quick demo of this so that it's really helping you. So this is Zotero, where I've been uh, marking a lot of notes around this. This is the paper, and in AI I just saved a couple of papers, but if I want I can drag drop more papers and so on. And if you are looking for alpha archive and so on, this is how you go and search for papers. Okay, let me go to the home. So this is me going home. This lists a couple of papers, but if you want a particular papers references or similarities with other papers, this is a very good tool. So you go to alpha.xiv.org, you select a paper and then go to the similar tab. It lists you all the similarities with other papers. For example, currently I'm looking at masked visual actions for unified world modeling, and then there are competing papers, uh, closely referenced papers or similar papers that we can see. Yeah, so that's where these foundational tools help us, and it helps us understand this context, the research paper better. Coming to the AlexNet, which is where we discuss about the paper published in 2012 by Krzyzewski, Sitzkewer, and Jeffrey Hinton, yeah, who's called the uh, godfather of AI. Yeah, these people participated in a competition called NeurIPS, which was based on the ImageNet dataset, and they won that year. The reason they won was that they had the largest single year jump in the error rate in ImageNet's history ever. Yeah, so that's what we are going to look at. We're going to dive deep into the patterns, the trends that it said, the innovations that it brought in. Nothing about stimulating the whole paper again. Yeah. Fifi Lee started working on a data collection set called ImageNet, and through the Mechanical Turk uh, framework in AWS, she was able to get many people to label these images that were collected from internet, and they collected over 15 million images with over 15,000 classes. I believe it is over 10,000 classes in total. But for ImageNet competitions, they were giving 1.2 million handheld label images with 1,000 classes. Yeah, this was an annual competition that was being held. Yeah, at some point in time around 2009, 2010, they started seeing a saturation of the error rates. Error rates could not move beyond a certain limit. Yeah, and before 2012, how they were winning these competitions was simple. They were hand engineering all the features. They were saying, hey, these are the features to look up, and they were giving a human designed detector, a sift or a hog process that turned pixels into numbers. Okay, and these were all shallow classifiers that learned only the top features, and hence they saw that the progress had stalled around 26% for the top 5 error rate. So ImageNet looks at top 1 and top 5 error rate. How does it work? Top 5 error rate says that if a particular image is given, the model should be able to predict top 5 categories or classes that the image could belong to. Okay, and one of the answer should be in the top 5. If it is not, it is an error, and that's what top 5 error means here. Yeah, and reaching only until 26%, as in 1 in every 4 images were being errored. The ceiling looked real, as in it looked very bad. Today we are very close to maybe 95, 96%, but at that point in time 26% error rate was pretty good, and they had hit a ceiling. They were not able to improve beyond that. I wanted to hold this framing for a second because the representation was designed by hand and the progress had stalled. That is the setup for this entire lesson. Yeah, pixels were being human designed for shift and hog features, and they had built a shallow classifier which led them to a top 26%. But AlexNet, uh, 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 belonging to the Jeffrey Hinton team, they did something different. They chose 8 learned layer convolutional neural network with approximately 60 million parameters, and they trained for 6 days on two GTX 580 gaming GPUs, approximately 6 GB, 3 GB was each on each GPU, and this was happening in Krzyzewski's bedroom actually. Okay, they didn't have a proper place to put this and train. And for 6 days it was training on all of that 1.2 million images. There were no hand built features. The network learned those edges, the texture, the object part, and everything. Yeah, it learned them straight from the pixels. The result, 15.3% of top 5 error rate in the competition. Big difference between the second place and the first place. The whole industry was stunned. Okay. The room understood instantly that, hey, the plateau wasn't a property of the problem, it was a property of hand designed features. Within 3 years, essentially every ImageNet entry was a deep net. It influenced the industry so much. Yeah. Yeah, I believe for differentiation, we could always say that Hinton's DNNR research was immediately auctioned and Google purchased it. Yeah, such was the demand for talent and compute people and companies then. Yeah. AlexNet's success can be decomposed into five very addressable or very nameable ideas. Okay, one, rectified linear units. These were the activations that these people had done differently. Yeah, what they did was, instead of using sigmoid tan h, which is a function, yeah, they used a different function. Yeah, it helped them learn uh, faster by 6 times. Okay, instead of taking 32 to 36 hours, they were now just taking 6 hours to train the whole model. Yeah, and this was cheaply sidestepping the vanishing gradients as well. Yeah, and since then this is the default activation unit being used. GPU training, the earlier everybody was on CPU, these people started using GPU. Two GPUs were used. This was the origin of AI improving NVIDIA by infinitely. Yeah, NVIDIA until then was purely a gaming chip. um, at least this was in 2009 2010. So I remember my friends uh, gaming extensively on GPU enabled boxes, and these boxes are hardware were very costly then, and only the kids with the lot of money they used to purchase this. Yeah, gaming hardware was repurposed and it was all for matrix multiplications. Nvidia's chips then for GPU were primarily to render the images on the screen, and they were good for doing these small computes on screen, and hence it also supported AI challenges where we needed a lot of matrix multiplications. Yeah, small, very small compute, but uh, mm, parallelization was important. In parallel we had to do hundreds and thousands and millions of computations. Yeah, dropout was another interesting thing that they did. Yeah, they randomly picked certain neurons and zeroed them during training. Yeah, what did this do? This avoided overfitting. Yeah, and that's why it helped us to co-adapt for regularization. Yeah, data augmentation was another thing that they did. They took the images, they flipped it, they cropped it, they changed the color variants and so on, using a few scripts, and that's how they augmented the data a lot. They were able to generate multiple sets of data, pass through the same model to reduce overfitting. Yeah, the first time you see data treated as something you design, not just collect. It's a lever, it's not a given now. Yeah, and these crops and flips actually manufactured that free training data that they wanted. Yeah, in this case the depth mattered. The number of layers that they had for this convolutional neural network was very important, because even if they had dropped one layer, the performance got worse. Yeah, the 4 out of 5 things that are we still using in 2026 comes from AlexNet. Yeah, why it changed everything? Because they said that, hey, learned features will beat always this hand engineered features at scale. Yeah, we need not understand the features in the first place. System can identify those required features and do it. Yeah, this was not a better classifier. Yeah, this was altogether a different philosophy of where representations come from. Yeah, and it was settled by a number no one could argue with. Yeah, 15.3%. Yeah, and when it was published in 2012, this dominated the research until 2017 also, where products built based on this paper were coming out in huge numbers. That's the difference. In 2 years, while it dominated the research, to 5 years in 2017 when it started producing products. And that's what we are saying, the future, the products were from the past papers. Yeah, for example, if you take this AlexNet, what it did was it brought in products today that we use, like face unlock, your photo search that you do, automatic medical imaging, autonomous driving perceptions. All these are built on AlexNet's philosophy. Yeah, it was commercialized at a scale within 5 years of paper coming out. Yeah, such was the scale of innovation at that point in time. The transferable read is this: hey, when representations become learnable or the features become learnable, the moat leaves the hand crafted artifact. Yeah, then feature engineering was a big job then. Many people were applying for something called feature engineering, how to identify the features given for vision models. Yeah, and that totally got bust because of this. The job went away because they said we don't need feature engineering anymore. Yeah, every phone that unlocks your face, every app that finds beach photos, every quality inspection camera on a factory line is downstream of these two gaming GPUs running in that bedroom in Toronto. Very interesting. And word to vec did to language what AlexNet did for videos. Miklo and team from Google, they taught us that lessons can be repeated just 1 year later and in totally different space, which is language from vision. Yeah, they derived this from a code that was coded by somebody saying that, hey, a word is nothing but uh, uh, the company that it keeps. And this word's meaning was all the context that we carried forward. Yeah, you take a text corpus, you identify the nearby words that define the meaning for that particular word, you train that using a certain techniques called SIBO or skipgram. SIBO is continuous bag of words, and you learn or build the embedding matrix. This is the most important one. And in that matrix, similar words occupy the nearby positions, and all these embeddings become the inputs for downstream natural language processing tasks. That's all the thought was. Yeah, you take a word, you create a vector out of that, and that vector needs to be put using one of these two strategies in an embedding matrix, and similar to certain words. And when some need arises, you pull that word out. That is all that RAG applications do today. Yeah, that's all they do today. This was the move. We learn a lecture from every word such that the words appearing in similar context get similar vectors. Yeah. Nobody hand defines what king means. And the model infers it from millions of sentences it appears in. Yeah. Meaning it is learning from data. The same AlexNet lesson that is transposed to language. SIBO versus skipgram versus negative sampling. All these are strategies on how you index the data, how you embed the data using vectors, and how do you create these vectors. Yeah, SIBO, which is a continuous bag of words, helps us predict the center word from the surrounding context words. We are going to look at a certain example in the next page, so please bear with me for a second. What it does is it takes a surrounding words and predicts what's the center word. That's how it learns. All the embeddings learn in that way. The trade-off is that it's fast, it smooths over frequent words. You look at skipgram, it predicts the context word from the center word. You take the center word and it predicts the left and right words. Yeah, that's how it's learning. This is slower because there are so many words to be learned for each word. Yeah, but it is better for rare words because the context on the left and right is very important. Now it learns a little better compared to SIBO for rare words. Okay, not the regular words, but for rare words. Negative sampling, the follow-up trick that they used was, hey, instead of a full softmax over the entire vocabulary, just discriminate a true context pair from a few sampled fake ones. That's all they did. From the few sampled fake ones, they discriminated a true context pair. It picks this one and rejects the other ones. Yeah, that's all it was trying to do. It was trying to do negative sampling. Okay, making training tractable at scale. Yeah, file under engineering pragmatism beats elegance. Yeah, you quickly try to solve it instead of going for elegant solutions. Yeah, because it was too slow. Yeah, full vocabulary softmax that the other tools were using, it was very slow. Yeah, the cheap approximation that made word to vec trainable was the real innovation, which is negative sampling. Yeah, we will see this again and again in techniques like quantization, where large models are reduced in size to small size models. For example, DeepSeek, you would have heard that they had a uh, 64 billion parameter, how they reduced it to 16 billion parameter, to 8 billion parameter, to a 4 billion parameter. Yeah, how did they do that? That's quantization. uh, Sorry, when I meant in billions, I also meant in the size, because quantization helps us reduce the size. Yeah, and distillation and caching. Yeah, so the interview note that we should all remember is SIBO was able to predict the word from context. It was fast. Skip Graham was able to predict the context from the word, that is, predict the words surrounding it. Yeah, from the center word. And this was working on rare words. So this is a good example. Suppose there is a sentence that goes like, she is a dash dancer. We are trying to predict the center word from the other words, the context words. This is SIBO. Yeah, continuous bag of words. You have continuous bag of words in that you are trying to predict one word. Skip graph, you take one word and predict the other words surrounding it. How do you do that? You train it. Yeah, for example, if there is a word called the, and it has quick and brown as the neighboring two words, because the window size is 2. If you add window size 3, it will go till the quick, the brown, the fox. Three collections will come. So these training samples were fed into the machine learning model for creating the embedding model. And that's what gave all these words meanings. Yeah, for now what you could do is you can understand that there is a vector called king. If you could subtract like a vector called man and add a vector called woman, you could arrive at a vector called queen. This meant you could do arithmetics on words. For example, you could find the capital of a particular country based on an example. You could identify past tense for particular words. We were never teaching all of this, guys. This was being learned by the system because we processed it in a certain way. Yeah, and similarity becomes a product primitive, as in how similar are those two things now becomes how close are their vectors, because we have moved away from actual meaning to their vector form, and in vector form we only need to understand how close are they, and it becomes cheap and computable. Yeah, this is where we talked about cosine similarity in track A, if you remember. Find king or queen yourself in the TensorFlow. Let's take a quick walkthrough of a tensor. Yeah, a tensor that's been. So if you want to view this, go to project.tensorflow.org, and in that you can go and search for the word king here. If you see the word king is here, and somewhere in this data set there is a word called queen. Yeah, you see here. Oh, did I spook it? Oh, what did I do? Huh. Crowd. There are kings as a word here. There is prince. There should be princess. For example, wife is here, grandson, daughters. And we just saw that queen also was there somewhere. Yeah, if you keep searching, you're gonna find it. I'm not gonna waste your time. See here. You see something called queen here. It's not surfacing because it's way below, and yeah, here that word was there. Yeah, so you could use this project tensor workflow to look at it. Coming back here, um, yeah, from static vectors to R in the G, and that's what we are doing today, right? We are using RAG as an application to surface the data from a corpus of documents. Yes. How it all started? Word to vec, which was a static representation of all the data. Then we started using glove as a process. It was still static. Then we went into contextual embeddings. This is where it all changed, guys. Elmo and Bert were now saying, hey, your words need not be understood. Now you can define vectors that now depend on its sentence. Instead of a word, it will be a complete sentence. Yeah, words vector now depends on its sentence. Where in the sentence is it available? And that became sentence embeddings. And this is how the whole embedding models changed. And embedding model APIs now that were developed by recently by OpenAI, Cohere, Voyage, and others are living on the same model on sentence embeddings developed by Elmo and Bert. Okay, based on all of this, your vector DBs, your semantic search, the retrieval concept in retrieval augmented generation all came into existence. Yeah, the key upgrade: word to vec was static, bank had only one vector. Now what in 2018 Elmo and Bird did was they made it contextual. That is, the word vector now depended on its complete sentence. So based on sentence, the the the, the bank as a word, which could be a river bank, it could be a bank where we keep money, they have different meanings, right, based on the sentence. So their position or the vectors for them changed. Now the primitive is unchanged. That is, representing a meaning as a vector did not change. Okay, it is still being compared by distance. But every vector DB and RAG system now descends from this 2013 paper. All your semantic search, recommendations, deduplication, clustering of data, retrieval of data, the R in RAG, which is retrieval, traces back to this example. King minus man plus women is equal to queen. This brings us to the next section, which is the shared lesson. What did these two papers teach us? Yeah, and that's what we're going to look at. Both the papers came 1 year apart, and they taught the two same things are two modalities. Stop hand engineering. You don't have to feature engineer the data, yeah, for model training. Let models learn the features from the data. Hand-built image features shift hog and hand-built word meanings both fail to learn vectors. Yeah, it's the founding move of our and your era. Yeah, attention and transformers are better ways to learn representations. BERT and GPT are the idea that scale them up. Yeah, RAG is what you do once meaning as vector is cheap. Yeah, once meaning as vector becomes cheap, RAG is what you build. Yeah, a key takeaway that outlives these models is, hey, feature engineers were a profession, like I told in 2011, and they were gone by 2016. We learned that more data, more compute is the only answer. Yeah. Um, and these days, the question being asked is who has that data? Yeah. And if you were to build a collection of papers that you're going to read through these 15 weeks, I would suggest that you create a table something like this and keep a track of all those papers. And throughout this, look at what papers you're going to read, one sentence that these papers claim, look at what context existed before the paper was brought in and what happened after. Key methods deployed, one core move, no math, explain it like a PM. Okay, results, what single figure made the case? Yeah, AlexNet, for example, did a 15.3% error rate versus 26.2, which was the second best case. Yeah, second best error case. And why it won? This is what we need to prove. Yeah, or the paper needs to prove the philosophical point, not just the metric. Yeah, and what product lineages came out of this? Who commercialized the whole paper? What did they build out of that? In 2026, what is the key product that is being built on the idea or the paper that we are talking about? 3 PM takeaways. We as PMs, we need to understand that every paper presents us some learning aspects, but what will those key transferable lessons be that we are going to actually reuse every time? That we need to identify out of these papers. One thing that we will still not understand when we are reading the paper, so maybe we need to bring it to office hours, the community. Honestly, this is worth doing it, because while we are sharing the knowledge, we are also learning and growing together. Yeah, I would want you to fill both your papers, paper 1 and paper 2 that you're reading for this week, into these. I'm also going to do it. I'm going to share you by week 15th. Let's see who does that. Let's dive into the PM perspective that we need to bring in. We already saw that how to read a paper, what papers to begin with this week, but why should a PM read the source papers and the misconceptions that we have to kill. Yeah, what we're trying to buy is foresight, not the math, guys. We are not going to write these algorithms. We are not going to re-simulate the whole exercise. We are not going to compute the calculations in the paper. But what we are trying to do is, hey, by reading this paper, what do we understand? By doing this research, what became possible? Who has productized or built products? What died? And where is the trend heading towards in a year or two? That's important, and that's where product manager's job comes. We learn the pattern, we don't learn the model. What AlexNet and Word to Vec did was teach us one transferable pattern. It said, hey, hand built features have gone. Yeah, the moat now follows the data. The more data you have, the more the reason that you could publish the next paper. Yeah, memorize this. AlexNet has 8 layers, and you can't. You get the vocabulary for free. Yeah, you understand these words like embeddings, ReLU, dropout, augmentation, CBOW or skipgram, static versus contextual, the R and RAG. Yeah, the words that your engineers are using on a day-to-day basis. Yeah, this gives you a chance to read from the actual source, and this is the cheapest way to learn the whole language credibly. Yeah, and you can converse in the same language with your engineers as well, and that's more important for product managers. Here are some misconceptions to avoid. People think that by reading a paper you will understand the math. No, you have to understand the idea behind it and what consequences this leads to. Yeah, skip the proofs. Yeah, because pass to say so, but PM pass has no equations. You need to read it thoroughly. AlexNet was just a better classifier. No, it was a different philosophy altogether. It just did not classify items, but it told us that hey, you are learning the wrong way. Instead of hand engineering, you need to let the system learn the features in the first place. Yeah, and that's why it gave a 11-point jump. Yeah, the philosophy is the point, not the classification. Embeddings are a modern LLM thing. No, this was in 2013. Yeah, this is like 1957 all again. Every vector DB and RAG system is descending from word to vec. Nothing has changed systemically. Yeah, it as a pattern, as a learning, as a knowledge, it still remains the same. Word to vecs are contextual. No, they are not. They are static in nature. That is one word per vector. The paper that was later published in 2018 told us about Elmo and Bert. Yeah, they are more contextual embeddings. Yeah, this distinction is an interview signal because we are going to see how these are asked in interviews as well. The elegant method is the innovation. Yeah, often the pragmatic approximation is what made it shippable, is what we are saying, because of the negative sampling. Yeah, we need to watch for the affordability trick. What made it affordable was more data, was more compute. Yeah, before 2012 compute was costly. Before 2012 there was not enough data. Both became possible. These are history. My job is today's tools. No, today's tools are built based on those ideas, and these tools are scaled up. Yeah, and no scaling loss, RAG or NVIDIA story without the 2012-13 origin. You cannot talk about these without the origins. Yeah, I wouldn't say by heart the facts or the trivia, but understand the patterns. Yeah, the paper reading questions that drill until we become reflexive in nature. What's the claim? One sentence from the abstract and figures alone. What did it beat and by how much? This was the comparison, the 11 percentage, and the number that mattered. What became possible from that day? We all know the story. What died because of it? Where did the old mode go? Feature engineering is gone. What's the 2026 descendant? All the features that we spoke about, yeah, is from that gap. In an interview or a reading group, you might be asked or you could discuss this. That's the transferable skill from week one, guys. nothing more. If you're preparing for interviews, here are 5 questions and the model answers that could help you. Why was AlexNet a turning point? Because it said, hey, by feature engineering, you could only limit its learning, but by letting the system learn the features in the first place, by building a convolutional neural network on two gaming GPUs, you can hit or you will hit 15.3% error rate versus 26.2. This was that biggest single year jump in image net history. Yeah, within 3 years, every entry was a deep net, because everybody now had GPU and they were trying to train the models on deep neural networks. Second question: explain embeddings using king minus man plus woman concept. Yeah, so for us, in simple words, embedding is a vector per word. Yeah, static words we are learning, so the words used in similar contexts sit next to each other. Something like, if king, man, woman, and queen are all together, we could derive an equation saying king minus man vector plus woman vector would land approximately near queen. Yeah, we can do this arithmetic on meaning. Yeah, semantic relationships are directions in the space, male to female, capital of, all that relationships become practical in nature. What's the through line from word vec to rag? Yeah, if you look at it, we already spoke about that. Hey, it started with static word vectors, so word to vec and GLAW. Then it moved to contextual embeddings using Elmo and Bert in 2018 paper. Then it came to sentence embeddings, and embedding model APIs were evolved using Cohere and OpenAI and Voyage. And then we said, hey, how these came to evolve into vector databases and semantic search. And from here, we all know that this evolved into retrieval augmented generation, the evolution of LLMs coming into picture. Yeah. Because all the semantic search is nothing but retrieval in vector basis, plus semantic search is nothing but retrieval. Yeah, the primitive never changes. They represent the meaning as a vector compared with the distance, which is a cosine distance. Yeah, rag is what you build once that primitive is cheap and contextual. Yeah, the R, which is a retrieval in rag, is nothing but a direct descendant from that 2013 paper. SIBO was a skipgram. How are you looking at the words? How are you training the model? Yeah, two word to vec architectures are these: SIBO, yeah, and skipgram. SIBO predicts the center word from the surrounding context, which is faster in nature, whereas skipgram predicts the context words from the center word. It is slower but better on the rare words. We looked at this earlier. Uh, Predict word from context versus predict context from word. Trading speed against rare word quality. Negative sampling is the trick that made either trainable at scale. Yeah. Why are the two papers? Why do we teach the two papers together? Because they are teaching us a common pattern, which is that, hey, stop hand engineering, and more the data to learn, the better the system performs or the model performs. Yeah. The interviewer is actually testing whether you see the pattern above the two features or papers. Yeah, not whether you memorized either one. They're not asking you how convolutional neural network works, how many layers are there, how many eigenvectors were used, what softmax function was used, was it tanh, was it ReLU. They are not asking that. They are asking us, what pattern do you see? Because as a product manager, we need to see patterns, and that's the vocabulary we are going to own, guys. We are not trying to buy hard all these ReLU, GPU dropout, augmentation, etc. But if we understand these papers in depth, we can convey what led to what. Yeah, and that's more important for us as product managers. If you want to practice some of this, I would recommend that you go and set up the Zotero, which is the free open source paper paper reading come storage come tagging come many other things that you can do in Zotero. Use the a 3-pass technique on AlexNet, do the PM pass on the word2vec, tear down a particular product. What I'm going to do is I'm going to tear down how notebook LM works. Yeah, I'll take that one particular product and end to end understand how AlexNet or word2vec helped us build tools, processes, frameworks, and everything around Notebook LM, because that's one good product that's been built recently, which does a multi-model output at scale. So understanding that would really help us. I would also recommend that you write the meta lesson that you learn in your own words. That's really gonna help you, because it helps you put down the words in your exact words. If there is a gap, you can go and talk to friends. Yeah, and publish a cleaned up post, maybe on LinkedIn or X, explaining what did you learn. Yeah, don't forget that 10 field table that we have to create for each paper, so that becomes a discussion point in the future. This brings us to the end, and we are saying meaning has geometry now. As in, king as a word can be put as a vector in a space, and we could understand its relationship with others. Like J.R. Firth said, you shall know a word by the company it keeps. Yeah? These models are learning the features we used to design by hand, by themselves. We are not feature engineering them anymore. This was all as part of the Tracky Part 1 foundational papers. Talk to you in the next video. Thank you. One thing that I forgot to showcase, there are two good sites that if you visit, what you could do is you could visualize the whole paper that we were talking about. One is on this CNN explainer from poloclub.github.io. In this, they are showing the whole convolutional neural network. You could click on these elements to see the flow. For example, I want to see, hey, what is this uh, convolutional layer consuming data from? You see R, G, and B data coming in. It goes to a bias, it adds the bias, and so on. And you can click on these to see how data is flowing from various elements. Yeah. You could also click on these bell peppers to understand, hey, which of these layers are bringing in more data, and so on. You could scroll down to read more in detail, as well as they explain every aspect of this um, convolutional neural network. In track A, we saw how matrix multiplications are very important, and that's where in this convolution, where they are uh, doing a pass of elements across. As it passes across these elements, you could see a lot of matrix multiplications happening. You could understand how hyperparameters work. For example, input size could be reduced, it could be increased. Yeah, and how by adding a padding, how we couldn't do this, uh, and how by adding a padding to the whole of the element, it changes everything. You could increase the kernel size, you could increase the stride, for example, the number of strides that we have to do, because only the number of strides that we are going to do, only that many outputs will come. Again, something deep, but if you are interested, you could use this. The other thing is, if you're trying to understand word to vector, you could look at this page, which is J Alamar. It's written as Jalamar github.io, illustrated word to vec. And the same example that we looked at on king, man, woman, everything, that is exquisitely explained in this paper. This is in this page. It's really interesting because it goes very deep, and it's very long. It tells you, hey, what are the common elements, are vector points that we are looking at. It looks at how the language modeling is done, how the next text prediction happens using natural language processing, how the words are predicted, and so on. Guys, this is very, very, very interesting. If you have time, if you have the patience, go through this, because it also explains all the skip gram, and the cbow and everything. Very interesting, very interesting. You will not find such content anywhere else on the net. These two pages are highly recommended. Yeah, please go through them. Thank you.